Today we're going to be learning about the area between curves, but before we get to that we're just going to do a warm-up activity where we just kind of remember how to find the area underneath a curve. So I'm going to do warm-up 1A and 2A at the same time because they're the same question. One's asking to use geometry, one's asking to use calculus. So rather than me having to rewrite everything, I'm just going to kind of do A and A, B and B, C and C, and D and D. So let's begin. If we're using geometry for this one, we just first have to draw our little XY plane, and then we have to graph the function. So this is y equals 6, so that's right here, y equals 6. And then we're looking at this from an x value of 2 to an x value of 5. So this is the area that we're trying to find. That's what the integral is really asking us for. And this is 3, that is 6. So this is going to equal 3 times 6, so 18 units squared. Now if I answer the same exact question using calculus, I need to take the antiderivative of 6, so that's going to become 6x, and then I'm just going to evaluate that from 2 to 5. So I'm going to have 6 times 5 minus 6 times 2. So that is 30 minus 12, which I'm pretty sure is 18 units squared. So whether we use geometry or calculus, we get the same answer. Significantly easier to just use calculus, especially if we have something more complex than just 6. For part B, we're going to, again, use geometry, so we've got to graph this. I'm going to graph the line y equals x, and I'm looking at it from 0 to 3. Okay, so this area underneath the curve is a triangle. So I'm going to do 1/2 the base, which is 3, times the height, which is also 3. So I will get 9 over 2 units squared using geometry formulas. Now, if we were to use calculus, we're going to take the antiderivative of this. So that's going to be 1/2 x squared. And we'll evaluate that from 0 to 3. So that's going to be 1/2 times 9 minus 0. So we get 9 over 2 units squared. For C, when we graph this, we're going to end up with a trapezoid shape, I believe. Looking at this from 1 to 5, so I'm just going to evaluate this at 1. That's going to give me 3, and at 5 I'm going to get 11, and this distance right there is 4. So this is a trapezoid that I'm trying to find. So that's 1/2 base 1 plus base 2 times the height, so times 4. And that's going to give me 28 units squared. Using calculus on the same thing, I will get x squared plus x, evaluating that from 1 to 5. So that's going to be 25 plus 5 minus 1 squared plus 1. So that's 30 minus 2, which is 28. So same thing. D is slightly harder because we have two different integrals all at the same time. But we can basically find the area using geometry for this one and the area using geometry for this one, and then subtract those two answers. So if I start off with this one, it's going to be a line right here. So we'll have y equals x plus 3. And going from 0 to 4, so this makes a trapezoid shape, where that distance is 4, this is 3, and this is 7. So I'm going to have 1/2 3 plus 7 times 4, which is going to give me 20. So that's just the first one. Now when I do this second one with the 1/2 x, so that's going to look something like this, y equals x over 2. This forms a triangle shape, so it's going to be 1/2 times, let's see, when I plug in 4 I get 2, so it's going to be 1/2 4 times 2, which is going to be 4. And if I subtract these, that will give me the answer for geometry, right? So that's going to be 16 units squared. Now, visually, what we actually just found was this area right here that's bound between the blue and green curves. And that's the whole purpose of today's lesson. That's what we're going to be trying to figure out. How do we find that area? And we've already kind of set it up for us, but let's just look at this using calculus. There's two main ways that we can go about doing this. we can keep each integral separate, or we can kind of smush them together. It really doesn't matter. If I keep them separate, this one over here is going to be 1/2 x squared plus 3x from 0 to 4. And then it will be minus. And then this one's going to end up as 1/4 x squared from 0 to 4. So let's evaluate things. We're going to plug in 4. We'll get 16. Half of that is 8 plus 12 minus the 0. So I'm just going to end up with this little part right here, which is 20, which we already knew we were going to get. And over here, when I plug in 4, I'll get 16, a fourth of that, and I will get a 4. So when I do the 20 minus 4, I get the same 16 that we got over here. We could also combine these. So if I have x minus x over 2, that's going to actually just give me a single x over 2 plus 3. And since they have the same limits, we can just actually do it this way. So we could have just done 1/4 x squared plus 3x from 0 to 4, and we'll end up getting the exact same answer. So it doesn't really matter which way you write it, whether you combine these or keep them separate from each other. So before we get to the formal definition of finding this area between curves, let's just kind of break it down so we understand what's going on here. So I have a curve up here, f of x, a curve down here, g of x. I'm trying to find the area bound between two x values in this case. So it's this kind of really lightly red shaded area. And what we can do here in order to estimate is actually go back to our BFF Riemann Sum, which was the LRAM, RRAM, all of those RAMs. And we could just, I'm just going to pick an arbitrary one here. We could say, hey, I'm going to make a rectangle right here, and it has some sort of change in x values, and its height is going to actually be the f function minus the g function. Okay, so I can find the area of just a single one of these little rectangles by just doing f minus g times that change in x. And then if I just get a bunch of these rectangles and add them all up, which would be this crazy symbol here, that's going to give me an approximation for all of these. Now, if I start letting this delta x value approach 0, which is when we put a little limit in front of this and we say, hey, let's let delta x approach 0, this brings us to the real definition that we're used to, which is, remember that sums are really integrals. So we can have the integral from a to b of f of x minus g of x dx, and that this will equal the area between f and g from a to b. And this is essentially what we did in warm up 1D and 2D, where we had a function on top and a function on bottom, so we subtracted the top one from the bottom one, and that gave us the area in between those two curves. For example 3, they want us to find the area of the region between y equals secant squared and y equals sine from 0 to pi over 4. So let's just first sketch a really quick graph of this so that we have a nice visualization for what's going on. Secant squared is going to kind of look like this. If you remember, secant's graph goes like this and it kind of alternates. So secant squared is going to end up not having this bottom part, I believe. Don't quote me on that, I'm not 100% positive, but it basically looks like a bunch of u's going across the top. So that's going to be our secant squared. And then I think we're familiar with what sine looks like, right? It goes like that. I don't have my spacing 100% perfect, so I kind of apologize for that, but we're going from 0 to pi over 4 would be approximately here on the sine graph, so that's just where I'm going to put it, so 0 to pi over 4. And this is the region I'm trying to find the area of. So I'm just going to take the integral from 0 to pi over 4, so that's my region that I'm trying to find the area of, and then I do the top function minus the bottom function. So that's secant squared x minus sine x dx. So if we have a calculator, you could just type this in your calculator in radian modes. If we didn't have a calculator, we can pretty easily do the antiderivatives for this one. So let's just do that. We're going to end up with tangent x and then plus cosine x, and we're evaluating this from 0 to pi over 4. So we're going to have tangent pi over 4 plus cosine pi over 4 minus, remember the parentheses here, tan 0 plus cosine 0. So tangent of pi over 4 is 1. This is the square root of 2 over 2. tangent of 0 is 0, and cosine of 0 is 1. And I distributed that negative sign through, so the 1's cancel, and I'm left with square root of 2 over 2 units squared. It's not so bad, right? 4 is a little bit trickier. When we do our quick graph of this, so I have 2 minus x squared, so it's upside down parabola that's shifted up 2 places. So that's going to be something like this. So y equals 2 minus x squared. And then I'm pretty sure you know what y equals negative x is. It's going to go like this. I need to extend my green line here because I can't see everything. My bad. There we go. So what we're trying to find the area of is this area between these guys. So it's going to start from this point over here, and it's going to be this whole region here. And when we go to set up our integral, that's not going to be too bad. We're going to have the top one is the green one, so we'll have 2 minus x squared minus the negative x, and that's what we're doing dx. But we don't know what our intervals are yet, so we need to do some math to figure out what these intersection points are, and more specifically, just the x values. We really don't care about the other parts of it. So we gotta do a little bit of math, and I'm just going to set them equal to each other. So I'll have 2 minus x squared equals negative x. That's going to help me figure out when they intersect. So that gives us x squared minus x minus 2, I believe. And from there, we'll have x minus 2, x plus 1. So I'm going to get x equals 2 and negative 1. And those are going to be the bounds that I'm going to be integrating on. So from here, again, if you have your calculator, we would use our calculator. If we don't, it's very simple for us to just figure this out. I'm just going to rewrite it so that it's in the descending order. So I'm going to take the antiderivative of this. That will give me a negative 1/3 x to the third plus 1/2 x squared plus 2x. And that's a negative 1, and that's a 2. And from here, I'm just going to plug in 2 and plug in negative 1. I'm going to cheat and not do any of the extra math to show you that it works, but I got 9 over 2 units squared. So that's the area here. So a little bit harder because we had to first find the limits to the integration. For example 5, we're going to use the calculator to help us figure out the area in between these two curves. So I've gone ahead and graphed them in y1 and y2, and you can see the shape here that I have replicated on the answer key, and I need to find these intersections. I need to be able to store them, and that's a little tricky thing that we haven't really done before. So let's start off by just, finding the intersections of one of them. So I'm just going to do, second calc intersect, and I'm just going to find one. It gave me this one here. So what I'm going to do is just immediately quit out of here and then hit second answer. And it actually gives me the value that it just found. And I'm going to store that one as b because that's the upper limit. And I'm just going to go back into the graph. I'm going to try to get closer to that other one. So I'm going to guess that it's near negative 1. I just want to be closer to it. So when I do second calc intersect and I hit enter 3 times, it will give me that one. I do the same thing. I'm going to hit second quit and then second answer. And that gives me that one. And I will now ask it to store that as A. So now that I have these stored as A and B, I can just use the calculator to help me figure it out. So I can hit just math. And I'm going to go all the way down to this one down here that says fn int. So that's function integration for us. And if you have fancy type like me, then it's pretty easy. I'm just going to go from A to B. And then I can just type in the two equations. You actually can use vars because they're in the y variables, so you don't actually need to write it out, but I just will. It's just as easy. Minus parentheses x squared minus 1 close parentheses. Then you need to do comma x is the variable I'm integrating for, and then the bounds. So, sorry, I'm not paying attention to the fact that this is the fancy type. My bad. Just over here I need to put an x. I started to do the old school way. So if we have an older calculator, you need to do comma x, comma a, comma b. This looks like it should give us the answer. I hit enter, and there you go, got it. So on the AP test that you've already taken, if this were to have been on it, you would have to use exact values. So now you know how to grab exact values from the graph. Okay, for 6, we have the region bound by the square root of x, the x-axis, and the line y equals x minus 2. So I'm going to start off with the graph of the square root of x, so that's chilling right here, y equals square root of x. The x-axis, I'm not going to bother writing in here. Then we have the x minus 2, so nothing is drawn really to scale here, so I kind of apologize for that. And I'm not going to label everything, I'm just going to do that. Now, since we are being bound by the x-axis, I'm going to stop it right there. I'm not going to actually extend this line further down. And this is the area that I'm looking for. And we have some issues going on here, because when we go to do top minus bottom like we've been doing, well, this thing needs to stop right here. So for this part of the area, the x minus 2 is not the lower function. So we can't be subtracting that part from it. So we're going to break this up into this area, which is just the normal stuff that we're used to, which is when we're bound by the x-axis. So that's going to be the integral from 0 to wherever this value is right here, which is at 2, 0. So I just figured out when is that equal 0. So I'm going from 0 to 2, the square root of x dx, and that's going to give me this first area. To find the next one, I'm just going to use red, even though we already kind of have that here, b. Now we can use our top minus bottom. So I'm going to have square root of x minus parentheses, important, dx. It's going from 2, and then I need to figure out what the intersection is here. So I would just set these things equal to each other, and when we do that, we end up getting 4 is going to be that intersection point. So now we can just evaluate each one of these guys separately. So I'm just going to do all of that magical work. I guess I could show you the antiderivatives, right? Remember that that's going to be 1/2, so this is going to be x to the 3/2, so 2/3 x to the 3/2 minus 1/2 x squared. This will be plus 2x, and this guy's going to be the same, the 2/3 x to the 3/2. So when I do all of this stuff and I evaluate from 0 to 2 and from 2 to 4, I add them all together, I get 10/3 units squared. Okay, so that's what this region is. So example 7 uses this exact same scenario, except that it says, hey, we could probably use some geometry to help us out here, which is we can pretty much ignore this extra line here if we recognize that it actually forms a little triangle right here. So I'm going to call this one C, and I don't need to separate this one now at all. And what I can do is basically find this area under the curve of the square root of x going all the way from 0 to 4, which is that value right there. And then I can just subtract the area of this triangle. Okay, so I can just say area of that triangle. So this kind of combines what we did in the warm-up with kind of the new stuff. So we take the integral using calculus, and then we use old school geometry to help us figure it out. So let's just do this one out. We'll get that 2/3 x to the 3/2 from 0 to 4 minus 1/2 base times height. So let's see, this is 2, and this is also 2. Almost did that one wrong. There we go, 2 and 2. So when I plug this stuff in, I'm going to get, let's see, I'm putting 4 in here. This is a square root of 4, so that's 2 to the 3rd. That's 8 times 2 is 16/3 minus 0 minus 2. And when you do that lovely math out, that's 6/3. This is going to be 10/3. So we get the same exact answer we got in part 6, which makes sense because we're doing the same exact area. So I think this is the second number 7, so my bad, I think I messed up that. But what's going on for this one is another way that we could integrate, which is that we don't have to always go vertical. We actually can go to the y-axis. So it's the same idea that we had in the beginning with the x guys, where we have two functions, but this time if our functions kind of go more vertical, okay, so this one would be like a function of y, and this one would be a function of y, we can actually subtract as their distance away from the y-axis instead of their distance away from the x-axis, so kind of the opposite. And it makes finding certain areas much easier. For example, this same one that we've been working with, if we look at it from the y perspective, we actually do have a very clear one function on top, which is the purple one, and one function on bottom. So what I'm going to do is just solve both of these so that they're x equals equations. So this one's going to become x equals y plus 2, and this one's going to be x equals y squared. And now I'm going to integrate with the y values. So I have a y value of 0. This is a y value way up here of 2. Okay? And I'm going to integrate with respect to the y functions then. So I'm going to go from 0 to 2, okay, for the y values. And then I'm going to do the one that is further to the right, which is going to be the purple graph. So that's y plus 2. And then I will subtract the closest one, so the one that's more on the left, which is this y squared. And now I'm integrating with respect to y, so I'll put dy there instead. And now everything is exactly the same, we're just dealing with a different letter, so I'm going to have 1/2 y squared plus 2y minus 1/3 y to the third from 0 to 2. Plug in all of those numbers, and what do you know? We still get that 10/3 units squared. So that was 3 different ways of solving the exact same scenario. In my opinion, this is the significantly easier one. You don't have to think about how to deal with this. So if you come across one where you have this kind of region where you have to separate it out, it might be easier for you to just do it with respect to y instead.